A pumping system consists of a set of elements that allowing transportation through pipelines and the temporary storage of fluids, so as to meet the required specifications of flow and pressure in the different systems and process. In this unit we are going to see pump operating line, pumps in parallel and in series, installations with common point, and regulation of flow. In pumping, we can find with tanks, pipes, valves, and pumps, the basic specification that must satisfy a pumping system is to transport a flow of a given fluid from one place to another. Moreover, it is often necessary that the fluid arrives at the destination at a certain pressure, and that the system allows a range of variation of both the flow and pressure. The design of a pumping system consists in calculating and selection of the piping, pumps, etc. that would meet the specifications of the most economical way possible. The first section of this unit is the functioning of the pumping line. For this we will start with the calculation and explanation of Harisi installation, where we can see two tanks, the tank 1 and tank 2. The objective is to determine the operating point of a given pump that allows transport of fluid since tank 1 to tank 2. To do this, we begin by calculating the load heights H1 and H2 tanks, starting from the equation. In most cases, the height of the pump is usually provided by the manufacturer, but also can be calculated as the height provided by the difference between the suction flange and the impulsion. But the fluid does not flow ideally. The installation prevents fluid transport. This resistance results in what is known as losses, which can be linear losses caused by own pipe, and singular losses caused valves, changes of direction, a changes section. Once calculated loading heights and applying the energy balance, we obtain the equation. Our purpose is to determine the operating point, pressure and flow of the pump. For calculation of the operating point, we have to calculate which is the flow rate, which equals both members, and beginning this flow, calculate the height. There are two methods to solve. Graphically, this method consists in represent the graphs of installing and pump. The cut point of the two curves will be the operating point. Numerically, it is an iterative method. First is supposed to flow, once it is assumed a calculated Reynolds pipe to determine the coefficients of loss, calculated losses. You get the loading height of the installation, which equals the value of the loading height provided by the pump with the supposed flow. If the difference is admissible, the iterative method stops. If not, supposes another flow. The performance is stable if fortuitous leap is produced in operating point. The changes produced tend to return the system to the original point. In this case there are two intersections, A and B, but only B is stable. We are at the point B. We suppose that there is a brusque demand flow passing B1. As losses increase, and the pump gives less height, the flow is decelerated, returning to point B. Whereas if the flow rate decreases, past to B2, reduce losses, and the pump gives more height, flow accelerates, recovering and returning to point B. Now we're at point A. We suppose that there is a decrease in flow. We turn to A1, decrease the losses. But in this case the pump gives less height and the flow is decelerated, and does not return to point A and is slowing down. while if the flow rate increases, pass to A2, increasing losses, and the pump gives more height and the flow accelerates, then the flow does not return to point A but gets to the point B. The second part of this unit is pumps in series and parallel. It usually groups sets of pumps to provide adequate service to the demand when a single machine cannot do. Let's start with the pumps in parallel. Parallel pumps are used to ensure minimum reserve with a pump pumping if another fails. Operating losses at partial flow rates. Use pumps in series. Enlargement subsequent pumping capacity of a facility. For the calculation of the equivalent height provided by the two bombs, we represent the curves for pump 1 and pump 2, and the values are summed horizontally. The operating point will be the cutoff point between the curve of the installation and the curve of the equivalent height, giving optimum height, which is the same for the pump 1 and pump 2, and giving optimum flow, which is the sum of the flow rate through the pump 1 and the flow rate through the pump 2. To determine these flow rates, have to substitute optimum height in each of the equations of the pumps. The second provision. Pumps in series are mainly used to increase the height of total impulse. For the calculation of the equivalent height provided by the two pump curves are shown for pump 1 and pump 2, and the values are summed vertically. The operating point will be the intersection point between the curve and the curve installation of the equivalent height, providing optimal flow, which is the same for pump 1 and pump 2, and providing optimal height, that is the sum of height of the pump 1 and pump 2 height. To determine these heights, we must replace the optimal flow in each of the equations of the pumps.